out and it still may not move, right? Exactly, like torque. So the idea here is that all I want you to see is that this picture, I'm about to show it to you in an animation, but the idea is that we have forces pushing on this paddle wheel, all right? And we just need a basic understanding of what happens. So let's talk about curl. The first thing is to understand that we are defining in this section two operations on vector fields. So if someone hands you a vector field, we have these two things called curl and divergence. Curl, when we take the curl of a vector field, okay, when we do that, the answer is a vector. When we calculate what's called the divergence of the vector field, we're going to get a number, a scalar. And what they mean is what I'm going to try and show you, all right? And then I'll show you how to compute them. Or you know what? I'm going to show you how to compute them first. Well, what do you want to see? The computation, or you want to know what they are first? Yeah. You want to know what they are? Okay. Curl. I'm going to do the two-dimensional curl first. Okay, so let's say we have this vector field here, right? This is our vector field. So you can tell that, you know, in the middle, as we move away, right, as we move to the left or to the right, those force vectors get stronger. But they're all pointing in this direction, right? So right now, do you see that my paddle wheel is not moving? That's because the force on each side of the paddle wheel is equal. So what I want you to do is imagine that we're actually looking at a point. We're looking at a single point, and imagining these little, like infinitesimally small paddle wheels, and we just kind of stick them out and we see what happens. If we stick them out and nothing happens, the curl is 0. Curl meaning like twisting, all right, turning. So I don't want to twist. What's going to happen if I slide my point to the right? What's going to happen? I should start spinning which way? Clockwise? Let me try. Okay, you see that? Clockwise rotation. And I'm having the computer calculate the curl for us, which I haven't shown you how to do. Notice that our curl is negative. Yes? Clockwise, negative rotation. Then what would happen if I go to the other side? Should be counterclockwise, right? And my curl is 1.8. Now, watch what happens if I move this further to the left. What do you think is going to happen? Things will start spinning faster? So same direction? Same speed? Let's see. Look, 3.08. The curl got bigger, right? And it's positive, so I have counterclockwise rotation, bigger number, faster spin. So I like to kind of think of this as almost like, think of, if you can, a flat river, okay? This like sheet of water flowing. And let's say it's, you know, how deep is the water? It's only the depth of like one water molecule or something, all right? And so this water molecule is right here. All these other molecules of water are moving down the river with it. So if this little water molecule is going down the river, right, and he kind of sticks his arm out, the guys on the right side hit him, right? The left guys hit him, but not as fast, so he starts spinning as he's going down the river. And so he has this twist to him. And does that make sense? Okay, and so that's the curl of the point. Okay? That was a nice spin, too. You like that? Okay. And then what if I move him up? What if I move him up? Nothing should happen, right? Yeah, the curl's exactly the same, 3.08. Initial settings. Go back to the beginning. All right. Now, what if I change the vector field? So that was this. By the way, this was the vector field. I have it where you can change them. Let's do a more interesting one. There we go. So if I start moving, right now I have 0 curl. If I move this way, I'm getting positive curl. I move up, negative curl if I move up, changes a little bit. Did y'all notice that the wheel does spin faster when it gets bigger? You don't understand what it took to make it do that. Oh, did I stop there? I had almost zero curl there. Look at that. Right up there, I'm getting almost zero curl. It's turning. I don't know if you can see it turning. I'm going to draw a line right there. Y'all do see it turning? It's very slow, right? Very slow. All right. Understand geometrically the idea of curl. Okay. This is stuff you would use in like fluid dynamics, right? You want to know how your fluid's behaving. You know, is everything chaotic and spinning around, or is everything just kind of chill, sitting in one place, not wanting to twist? All right, I'm going to pause this because sometimes I bring my computer to its knees. Three-dimensionally. Oh, you know what? Go back to this. I told you that the curl was a vector, right? Okay, right now you can't tell it's a vector. And this right here is actually the magnitude of the curl. I should have told you that. This is the magnitude of the curl. The curl is actually a vector, and the vectors is coming straight out at you. In two-dimensional, your curl vector is always coming right out at the board. All right? The length of that curl vector is going to be a measurement of whether or not, or how fast it's turning. If it goes into the board, the rotation changes the other way. All right? But in three-dimensional space, all right, so you see this little thing up there in three-dimensional space? What that is a point. All right? The red line segment there is the direction of the curl. All right? And that yellow disc is the paddle wheel. So I'm not going to show you the vector, well, I can show you the vector field. There it is, but it gets in the way. Is it moving? I have curl. Is this playing? Oh, play. Okay, here we go. So if I let things go, if that point, you know, if that was a water molecule, now you're in a river and the river has depth and three-dimensional and you're a water molecule moving around in here, then if you were right there at that, you know, instant moving, you would have this sort of twist to you like this, right? As you moved. And so you would ask, okay, what happens if I change my placement somewhere in that field? Trying to get to a negative curl. It's slow because the computer is doing a lot of stuff right now. I don't see me getting negative curl. Oh, I'm sorry, I'm taking the magnitude of it. Oh well. You just have to deal with it. I think you get the idea. Oh, that's a lot. That seems a lot faster, right? Right? So you get more twist there. All right. Where are my computer science people? Any computer science people? There you are. All right, here you go. So there it is. That's not so bad. The hardest thing that I had with this damn code was getting it to draw an arbitrary circle. Circles drawn, if I tell you to draw a circle on a flat sheet of paper or this wall or on the ground, that's easy to do. But to draw a circle arbitrarily in space is difficult. It requires quite a few transformations to do it right. So, yeah. That's just encouraging for you later. You like code, there's code. All right, I think that's all I have. So let's actually get to the computation of curl. Well, the computation for curl comes from, we're going to use a cross product, okay, to define what curl is. But before I can define cross product, we're going to define this symbol right here called del to be equal to this. And it's right there, but I want to write it down here. This is different than anything you've ever really seen before. Because if I give you a vector, usually you want me to plug some numbers into that vector, or usually you want that vector to have like functions in it or something, right? Variables. This is a vector that we are defining to not be any of those things. The first component of this vector is what we call a differential operator. It's an operator. It operates on functions. You put this together with a function, and it takes the derivative of it with respect to x. You put this together with the function, it's going to take the derivative of it with respect to y, but it's not true multiplication. Do you see that? It's not like 2, 5, 7, then you just multiply numbers. That's not what's happening. You're operating. This tells you what to do. So this symbol represents the del, which is the differential operator. Okay. So curl is defined to be, curl, the way we write it, curl f, is defined to be the del crossed with the vector function f. And here's the standard notation for it. Del cross f. And we know from cross products that when we do cross products of two vectors, what we like to do is take the first vector, put it here, the second vector, put it here. And then this is our i's, j's, and k's. And our answer should be a vector. So to figure out the first component, we cover up this, right? And then we do a determinant right here, right? And then we cover up this and do a determinant, and then this and determinant, right? By the way, P, Q, and R, it's up here in the notes, are the component functions for the vector field, P, Q, and R, as they've been for a while now. Yes?
The order numbers?
What order?
Like del, cross, with f. Is another order immediately. Like f cross del.
You should get opposite signs, so this is the order you want to go with. There'll be parallel vectors. They'll be pointing in the opposite direction, though. So, but this is what I'm kind of making sure you understand. When I do this first computation, I do determinant, we say this times this, right? Do you realize that's not this times this anymore? It's the partial derivative with respect to y of this. So that's what this is. Minus, so going this way now, we normally say this times this, but again, it's not multiplication. It's the partial with respect to z of this, which is partial of q with respect to z. Understand? And then you keep going and finish off the rest of it. It's computational. There's no magic here. Or you just got to know how to do cross products and take derivatives. So let's find the curl. Find the curl of this vector field, and then find the curl. Then find the magnitude of the curl at a specific point. So the curl of f will be equal to del crossed f, which is equal to this thing, I hat, j hat, k hat. By the way, in the homework solutions for this section, which I posted today, I don't write I hat, j hat, k hat. I just do the two vectors. But following the book's notation, that's what they do. So this, xy squared. No, hold on. Oops. Let me give myself a little more room here. I need my del first. So del would be partial with respect to x, partial with respect to y, partial with respect to z. And then x squared yz, xy squared z, and xyz squared. Why don't you try that? See if you can get it. Okay, that enough time? Y'all got it? Okay. Try and do it without writing each one of them down like partial of this. Like do the computation if you can You know what I'm saying? Like if I do the first one, I'm going to do the partial with respect to y of this. Like do that mentally, if you can. When somebody gets an answer, let me know. I'm writing down on the board what I told you not to do, just so that we have something to reference just in case. Yes? Did anybody get that? Yes? Okay, that's your curl. Now, what is the magnitude of the curl? Well, find the curl and its magnitude at a specific point. So now, if someone tells me x, y, z, what I'm doing is I'm actually going to find, in three-dimensional space, if you go out to that point, I'm finding that red line segment. And if I take the length of it, it tells me how fast that yellow wheel was spinning. Okay? So that's my symbol for at. At the point 2, 1, 0, we have that the curl of f is equal to, it's a vector, 2, 1, 0. What do you get if you plug in 2, 1, and 0 for x, y, and z here? Negative 2. 4 and 0? Agreement? Okay, and then what is the magnitude of the curl? Root what? Root 20 or 2 root 5. Okay? What do y'all think? Pretty straightforward, just a computational thing? All right. I did a couple of those on your homework, and one of them very straightforward like that one. The other one was a little ugly, but I did work the whole thing through. All right, so what about finding the curl of this? And find the curl and then find the magnitude of the curl. What should you scratch your head about initially here? Yeah, didn't we say cross products, to do a cross product you have to have a three-dimensional vector? Yes? This is only two-dimensional, so how can we do it? So what we'll do is we're going to extend this vector field into 3 dimensions by making it a function of x, y, and z. I'm going to leave the x and y components the same, and by default, I will put 0 for the z component, and that's what I will always do if I want to extend a two-dimensional vector field into 3. That just basically flattens it out on a sheet of paper, which is where you were to start with. And then you can do your curl. So curl F, I think this one's going to go pretty quick. I'm going to write my notation this time the way I did it on the homework. What's the curl? Cover this up. Partial with respect to y of 0, 0. Take away partial of x squared with respect to z. Just 0. Sorry, I didn't see negative x squared. Just 0, right? Because you're treating negative x squared like a constant. So you're getting 0 there. And then when you do this one, 0. And when you get this one, negative 2x, so negative 2x. All right? What's the magnitude of the curl? Square root of 4x squared, which is actually the absolute value of 2x. Okay. Do you recognize this vector field? It's the first one I showed you where the arrows were going bigger on the outside, smaller on the inside. Do you remember at the center that I wasn't spinning? So when x is 0, what's my curl? 0, 0, 0. The 0 vector, right? Which means I don't have any spin. The magnitude would be 0, no spin. If I moved out to the left, right, it got bigger, curl. So you can see if I put a bigger x value, either negative or positive, I'm going to get a bigger curl, yes? But notice when I moved up and down, do you remember this? Nothing changed? You see how there's no y in here. So this curl is independent of y. And you can see it in here now. We've already interpreted it geometrically. Let me make sure I stop that thing from spinning. Okay. Definition here, it's kind of hidden in here. But in fluid dynamics, all right, this curl represents the tendency of the fluid to rotate, right, which is what I tried to already explain. If the curl of your vector field is 0, then there is no rotation, and the field is called irrotational. That word look familiar? I think that word's on your take-home test.
Yeah.
It is. This just talks about extending the vector field, like I just said. If you extend a vector field from 2 dimensions to 3, you just always let your z component be 0. Now, a major result of curl. Do you remember that if we had a vector field in 2-dimensional space, that we could check to see if it was conservative or not? And what we did was we calculated this and we said, are these equal? Remember that? But I said we could not do that in 3-dimensional vector fields. We now have a way. And here's the condition. That's it. That's all you need. If your curl is 0, if the curl of your vector field is 0, it's a conservative vector field. So everywhere in the field, nothing's rotating. Things can be moving, but nothing's, no little molecule is spinning around as it's moving. It's moving in the direction it's supposed to go without any influence from anything around it trying to spin it around. That's a conservative vector field. That's an awesome way to check vector fields, but you still have to calculate a curl, which is a cross product, and those can be a little bit buggy sometimes. Now let's talk about divergence. Divergence is another operation on vector fields, and we'll talk about what it means first. We'll show it to you. I have two ways of showing this. So for this one, I want you to look at, this is the same vector field we had earlier, right? That 0, negative x squared. We know that if we take this point and do little paddles, we can get this spin, that's curl. Divergence is something completely different. What it does is we try and imagine we're at a point, right? And we try and imagine opening up this little infinitesimal ball, this little epsilon ball like I was talking about earlier, just really like infinitesimal ball. Now I've zoomed in on it, here it is. If I look at all the points around this ball and pick some points, there's a vector at each of those points around the ball, right? There's a vector from the field. Here are all the vectors on that field. I've labeled them in red if they are going into the circle. I've labeled them in green if they are going out of the circle. So what does it look like to you? Looks like the amount going in is equal to the amount going out, right? And so they should cancel each other out, and you should get nothing. That measurement of how much is going in and how much is going out is divergence. But the ball, this little circle, remember that circle is actually infinitesimal, right? When you get to a single point, you can't really talk about going in and going out, right? But we can do a limit kind of, and that's where this idea comes from. So if I make this ball bigger, so it's easier for us to see it, all right? And we got the same going in and same going out. Now what's going to happen, what do you think is going to happen if I move this to the right? Do you think I'm going to have the same going in as the same going out? I don't know, let's see. You have your own guess. So what happened? They got longer. It's because the vectors over here are getting longer, right? But they're still canceling each other out, aren't they? Because the ones that are coming in are as big as the ones going out. So we're still getting the same divergence here. You can add more vectors if you want to see more vectors in action here. Take them away. You can zoom in if you want to take a closer look at them. And you can zoom way in. I'm just looking, I haven't looked at this in a long time to see what the hell I put together here. Okay, so this is a pretty uninteresting vector field, isn't it? In terms of divergence, it's pretty boring. The divergence is 0. It looks like everywhere, right? If I move this up, anything going to happen? No. Move it to the left. Div is always staying the same, right? All right, so let's change to a different vector field. And let's go to the initial settings here. All right, more interesting. How about that one? You think we're going to get some interesting things? Let's see. Boom, right here at the origin. Oh, crap. Div is 0 still. Let me see, zoom into that. Div is 0. Let me show some more vectors. No? Okay, well, let's move it. Up or down? Left or right? Left? There we go. Okay, so see, we got more red coming in. Like the number of vectors going in might be equal to the number of vectors going out, but it's the length of the vectors that's overpowering what's going out. So if there's more force going in, the force coming out is not as much. So it's almost like pressure, you could say. More pressure on this side than on that side. Make sense? What about if I move it up? Oh yeah, notice the answer is negative. The answer is negative because there's more going in than coming out. Moving it up. Oh boy, we've got a lot of Very, very long red vectors going into that, overwhelming the green coming out. You see it? Probably going to have to move to the other side. I don't know, can I get my div to be positive? Let's see, here we go. Oh, over here I've got some positive div. There we go. Let me zoom back out. I moved too far. I think you can kind of see it here. More going, the green ones are longer. That's kind of cool, huh? All right, what is this in three-dimensional space? Instead of on a flat piece of paper and a point and a little circle, it's going to be three-dimensional space, a point and a sphere, a little ball around it. Well, I took the time to go ahead and put that together a couple of years ago. Here it is. So remember, this is a point, right? This is a point. But I'm making this little ball around it, and I'm looking around all the ball, and I'm trying to figure out if I've got more going in than I do have coming out. And I'm not showing you the vector field here. Yeah, I can't show you the vector field. You just have to believe me that there's a vector field here, all right? So here it is. Oh, shit, our div's big, right? Got a lot of vectors coming out of this ball, and they're really long compared to the ones going in. Zoom in on this ball. Let's get more vectors in there. Right, you see them? All these little ones in here being overpowered by all the big ones coming out. What is that?
Looks like an asteroid.
An asteroid? Yeah. So like here we are, right? There's us right here. Yes. And we're probably thinking to ourselves, right? What are we thinking at this moment right before impact? Positive div. Positive div. Boom! It's over. All right. Let's move this thing around. Maybe we can get some negative div here. Oh, here we go. Something's happening over here in the field. Now we're getting negative div.
We're dodging.
Yeah. I think you get the idea. Yes? So in terms of, curl gave us our tendency of our fluid to want to twist, right? To turn, to curl. The div measures the tendency of the fluid to diverge or leave a point. So it's like, it's kind of difficult to explain. I know some of you have heard of divergence before. You have any other good? No? No? Okay, divergence, tendency of the fluid to diverge or leave a point. So if you're at the point, if you've got positive divergence, there's more of a tendency for things to flow away from it than there are to flow into it, right? So if you're at a point and you move a little bit off the point, most likely you're going to be moving away faster than you are going to